In the subtropical climate of Florida, the pool screen enclosure is a mandatory architectural defense against harsh ultraviolet radiation, airborne debris, and aggressive pest populations. For decades, the baseline standard has been the highly functional single-story pool cage. Recently, an entirely new luxury standard has emerged, the multi-story panoramic clear view enclosure. Side by side, the physical leap in scale, peak height, and architectural ambition is massive. Designing at this magnitude triggers an extreme financial reality, requiring rigorous engineering analysis to justify the ultimate price tag. A standard single-story pool cage requires a baseline investment of roughly $8,000 to $15,000. A two-story panoramic structure routinely exceeds $50,000 to $70,000. Looking at this exponential cost escalation chart, the investment requires scales non-linearly as enclosures get taller and wider. The rising price tag directly correlates to physical mass, hazard labor, and strict engineering mandates required to counteract wind load physics. To understand why these structures cost so much, we have to deconstruct the enclosure from the ground up and analyze the physical breaking points of aluminum architecture. A standard enclosure maintains its structural integrity by utilizing vertical support posts placed every 6 to 8 feet. The luxury enclosure removes those vertical posts, creating an unobstructed 40 to 65-foot span. This graph illustrates the physics of the clear span. Beam structural strength drops parabolically as the span length increases. Mathematically, an aluminum beam spanning twice the distance becomes effectively 4 times weaker. Standard 2x4 aluminum beams are perfectly safe hardware for short single-story spans.
Crossing a 65-foot gap without snapping requires heavy 2x10 extrusions or proprietary structural profiles like the halo beam system. Gravity relentlessly applies downward force. Thin metal bows under the stress, requiring a massive increase in structural thickness to hold the line perfectly straight. Achieving horizontal aesthetic freedom demands exponentially heavier, more expensive aluminum mass. The engineering challenge shifts dramatically when moving from horizontal roof spans to vertical height. When an enclosure scales from 10 feet to over 20 feet, the massive surface area of the screen acts like a ship's sail. This diagram models a hurricane scenario. The expanded vertical geometry captures massive kinetic wind energy. The primary threat is lateral drift. The structure sways, risking immediate buckling. Code requires lower horizontal chair rails and stainless steel hurricane cables to distribute loads and prevent twisting. Vertical expansion forces engineers to construct a heavily braced, tension-locked skeleton to prevent cyclonic implosion. The structure's integrity ultimately depends on exactly how the skeleton is anchored to the ground. Category 5 winds flowing over a massive 2-story roof generate extreme aerodynamic uplift, exerting vertical pull forces that attempt to rip the structure from the earth. This cross-section demonstrates how standard patio decks and thin pavers fail under extreme uplift forces. Standard decking automatically fails municipal inspections for taller structures. The mandatory engineering solution is excavating and pouring massive, custom-engineered concrete footers embedded deep into the ground. The labor, machinery, and material costs to tear through a finished patio and pour deep concrete add thousands to the final build. To counteract atmospheric physics, a premium 2-story enclosure must be structurally rooted into the earth. Even the thickest aluminum beams and deepest footers fail if the micro-components connecting them give way. Florida's coastal environment combines intense humidity with highly corrosive airborne salinity. Driving cheap standard steel screws into an aluminum frame triggers galvanic corrosion. The mismatched metals react, causing rapid rusting and inevitable joint failure. Surviving this environment requires specialized Nylo-Tec or 300 series stainless steel fasteners designed specifically to resist galvanic reactions. The screen mesh acts as a massive membrane that absorbs kinetic wind energy across the entire structure. This tensile strength comparison outlines the strict limitations of builder-grade fiberglass, which offers low wind ratings and rapid deterioration. Mega-view builds require extrusion-coated superscreen or polyester mesh, rigorously tested to survive impacts from 160-mile-per-hour winds. Compromising on the smallest screws or the basic mesh guarantees a catastrophic failure of the entire macrostructure. These structural physics are strict legal mandates, codified directly into the Florida Building Code. This regional breakdown shows the inland baseline for cities like Orlando, where surface friction from trees and buildings breaks up wind speeds. By contrast, coastal zones like Naples present an open terrain exposure category. Minimal wind friction subjects structures to 170 mile-per-hour cyclonic forces. In these high-velocity zones, premium builders mathematically prove their engineering calculations to municipal inspectors before a single beam is cut. Local geography dictates the baseline physical limits, making a coastal two-story enclosure the ultimate test of architectural compliance. Bringing all these variables together answers exactly what goes into a $70,000 enclosure. The true cost begins with invisible layers: engineering stamps, municipal permitting, and hazard pay for aerial scissor lifts. Next comes the tangible mass: superscreen membrane, thick 2x10 extrusions, and deep concrete footers. This massive stack of requirements entirely dwarfs a baseline single-story build. All of these isolated variables synthesize to create a finished, masterfully integrated architectural space. The premium price tag represents the exact calculated cost of absolute structural peace of mind in the face of cyclonic forces.